A conjugate occurs when I take a binomial, say the quantity x plus y, and I multiply it by the same factors, but instead of saying x plus y, I'm going to say x minus y. So in essence, all I've done was change the sign of my second term. Let's see what happens when I multiply this out. I'm going to use my rules for distribution, and I'm going to multiply x times x. And what will I get there? X times x is x squared, and then x times a negative y is a minus x y. Now I will take my y term and multiply it by the x, and then multiply it by the negative y. So y times x will be a positive. I'm going to say xy here. I'm just going to use a commutative property and put the x term before the y, the x factor. And let's say y times a negative y gives me a minus y squared. So notice that when I'm multiplying x plus y times x minus y, my middle terms here will negate. They will cancel each other out. And that's the whole idea of a conjugate. When I have a conjugate, my middle terms cancel out, and I'm left with squares. So when I'm dealing with real numbers, I'm going to have the difference of squares. Let's try another example. Let's try an example that says x plus 2, and we'll multiply it by its conjugate, x minus 2. Now when I distribute that out, when I crab claw that out, I'm going to get x times x, which will give me x squared, x times a negative 2, which gives me a minus 2x, positive 2 times a positive x gives me a plus 2x. There are my two terms that are going to cancel. And a positive 2 times a negative 2 gives me a negative 4. My middle terms, as we say, cancel, and I'm left with an x squared minus 4. My middle terms will cancel out, and I'm left with just the difference of squares. Now let's give it a quick example as to why something like that might be useful. Let's say I have an expression that says 2 divided by the square root of 5 minus the square root of 2. Rationalizing denominators is something of a lost art because of the fancy calculators we have nowadays, but we can use our idea of conjugates in order to rationalize a denominator. We can remove our square roots by multiplying the square of each number, but notice since I have a negative sign here, then I need to multiply it by the positive radical 2 there. What will that do? Well, radical 5 times radical 5 will, of course, remove the radicals for me, and the radical 2 times the radical 2 will remove the radical there and just give me 2. On the other hand, I don't want a radical in the denominator, so I need a way for my middle terms, my radical terms, to cancel each other out. And we'll get that here. Let's just take a look at the denominator. Radical 5 times radical 5 is basically radical 5 squared. Then I'm going to have a plus 5, radical 2, and then I'll have a minus radical 5, radical 2, and then my final term will be minus radical 2, that quantity squared. Now, again, our middle terms will cancel. That's the whole point of multiplying the conjugate. And radical 5 squared is 5 minus the square root of 2 squared, which is 2. So my denominator was easy to disassemble these radicals by using the conjugate. My numerator is still going to be 2 radical 5 plus 2 radical 2, but it's okay to have a radical in the numerator. Oh, let's finish that actually. 2 radical 5 plus 2 radical 2, and 5 minus 2 combines to 3. So we're happy. Let's take a quick look at what would happen if I want to use this idea of conjugates. and apply them to complex numbers. So far we've seen that real number conjugates combine to the difference of squares, and it doesn't matter if we're using radical numbers or integer numbers or variables or whatever, we're always going to get the difference of squares with the middle terms canceled out. What happens when we use complex numbers and multiply by the conjugates of them? Something interesting, actually. When I go to distribute the complex numbers, a neat thing occurs. We do the same thing. We're going to use the same strategy. A times a is a squared, a times a negative bi is a negative abi, and then my bi times a, and my bi times a negative bi, so that will be a positive a bi, and then a negative b squared I squared. Now, again, our middle terms here and here are like terms, and they do cancel out. They go away. And at least at the outset, it looks like I have the same thing, the difference of squares. Except, don't forget that the definition of the number I is that if it's a number that when I square it, I get negative 1. So I squared is a negative 1, which means the following. Yes, I have a squared, but I have a minus I squared is a negative 1 times b squared, and a negative times a negative gives me a positive. So when our real numbers are multiplied by their conjugates, we'll get the difference of squares. But when our complex numbers are multiplied by their conjugates, we will get the sum of squares.